Hey everybody, so in this video we are going to talk about something called similarity, and it has to do with what you learned in your last lesson about setting up a proportion. However, we're going to set up and solve a proportion using some shapes. So what we're going to talk about today is called similarity, primarily because we are talking about two shapes that are classified as what are called similar figures. So for two shapes to be similar to each other, there's a couple of characteristics they have to have. First, they both have to be the same kind of shape. So for example, in this picture, they are both triangles. In a second, you'll see an example where they're both parallelograms. So they both have to be the same kind of shape, but they have to be different sizes. So it's a little bit hard to tell, but this first shape over here on the left-hand side is just slightly bigger than the second shape. In the second example, it's a little bit more obvious, like which is the bigger shape and which is the smaller shape. They have to, their sides have to be increasing or decreasing by a proportional amount, which we call the scale factor. You'll kind of see what that is in a moment. And their corresponding angles have to be congruent to each other. So what I mean by that is the way that these shapes are situated right now, like this one is kind of like upside down compared to this one. But you'll see in a second when I kind of go over this shape more in depth that the angles, like the angle that's angle A in this first shape and the angle that corresponds to it in the second shape, they're the same measurement. So you don't need to know like what makes a shape similar to each other. You don't need to kind of be able to look at two shapes and determine if they're similar. What you're going to be looking at is you're going to be looking at different shapes and you're going to be given the side lengths, and you are going to have to determine what is the measurement of the missing side by setting up a proportion. So let's start with this first example. So we have this statement over here. It says triangle ABC. So if I look at the triangle that has A, B, and C labeled, that means triangle A, then I go to B, then I go to C. That's how I would read the triangle. I would start at this top point, then go down here to the right, then go over to the left. And it has this squiggle mark that kind of looks like the enye sign. If you speak Spanish, it kind of looks like, I don't know, just a squiggle. It's it's one of the keys on your keyboard. This means similar. So if you ever see this symbol, that means is similar or similar to. So it's saying triangle ABC is similar to triangle FDE. So if you look at the second triangle, if we follow that same order, FDE, that's kind of the order of how we're looking at the sides of the triangle. So if you're ever given two similar figures and they're not orientated the same way, you can redraw one of the shapes so that way you can see what it looks like. So what I'm going to do is I'm going to kind of redraw the example down here. So I'm going to keep ABC, triangle ABC the same, and we have that this side is 10, this bottom side is 13. We don't know what this other side is. And then if I draw the other triangle, I'm essentially going to flip it over so it kind of is orientated the same way, but I need to make sure I label the points in the appropriate order. So they did A, B, C, and they started at the top and then went down to the right corner, then over to, went over to the left corner, then over to the right corner. So F is going to be at the top, D is going to go over here, and then E is going to go over here. So now I've kind of like reorientated it so it looks like triangle ABC, but I need to make sure I put the measurements they give me in the same spot. So DF, this length right here is X, and DE, this length right here is 9. So when you have a problem like this, you're trying to figure out what is the value of X? What is the length of this side DF? Knowing that these two figures are similar to each other, they're supposed to be proportional, meaning that whatever we're doing to 10 to get X, we're doing the same thing to 13 to get 9. Like maybe we're multiplying it by some sort of decimal. Maybe we're multiplying it by 2 to double it. We kind of just have to look and see. So we are trying to look at what are we multiplying the values by in the first figure on the left-hand side to get the values on the second figure. So we don't know what we're multiplying times 10 to get X because we're trying to figure out what X is equal to. But if we look at the corresponding side to 13, so 13's corresponding side is 9 in the smaller image, we're clearly decreasing, right? We're going from a bigger shape to a smaller shape. So when we're trying to figure out, okay, what's the value of x, we know that we're gonna have to decrease 10 by multiplying by some sort of decimal or fraction, or dividing it by some sort of number. So one thing I like to do, because it's not quite so obvious, what are we multiplying 13 by to get 9? It's obviously going to be some sort of fraction or decimal because we're getting to a smaller number. I like to use like 2 different colors, and I like to kind of highlight the corresponding sides. So when I set up my proportion, because that's what I can do, I can set up my proportion to solve for x. So I know that 10 and x, they are the same sides, the corresponding sides of a triangle. So when I set up my proportion, I am going to set them up on the same fraction. So remember, with our solving proportions, we use the acronym FUNS: fractions, units, numbers, and then solve. So I'm going to set up 2 fractions, but they're going to be 2 different colors. So I know that 10 and x are one relationship, and I am going to set that equal to the other 2 corresponding sides. So 13 and 9 are corresponding sides, and they're going to be the second fraction I set up. And so I'm going to make sure I put 13 on top, because that is the what I did for the other triangle. I put the bigger, I put 10 from triangle ABC on top, and then I put x from triangle FDE on the bottom. So I need to put the measurement for triangle ABC on the top here, which is 13. And then I'm going to put its corresponding side for the smaller triangle 9 here. So now I have a proportion. 10 over x is equal to 13 over 9. And now I'm just going to use, I could try to look across, use my Crossroads method to see if I can solve. It's not very obvious what I have to multiply 10 by to get 13. Again, it's going to be some sort of decimal. So I'm going to use the cross multiplication method. So if I use the cross multiplication method, 9 times 10 is 90. 13 times x is 13x. And so if I use my property of equality, 13 times x, I'm going to use the division property of equality to solve. So x is equal to 90 over 13. If we want to put it as a mixed number, that's going to be 6 and 12 13ths. So this particular side of the triangle is not going to be an integer. It's going to be a decimal, 6 and 12 13ths, which if we look at the 2 triangles based on like their size and shape, that kind of makes sense. Clearly we want to get an answer that's smaller than 10, right? If we got an answer that was bigger than 10, that wouldn't make sense because this is a smaller triangle. So what we did was we set up a proportion using corresponding sides of each shape, and then we used our property of equality, what we know from solving equations, to get our answer. Okay, so this was an example. I would say this is probably the harder of the 2 examples I'm going to show you. A, because we had to redraw the shape, and then B, we had to use the cross multiplication method, and our answer didn't come out to be a nice whole number. Let's look at maybe a little bit of an easier example. So the second example, I have given you 2 parallelograms. I did not label them with letters. You can just already see based on like the information that I'm giving you that they are similar figures. They're the same shape, but they are different sizes. They clearly have corresponding sides to each other that will be increasing or decreasing at a proportional scale factor. And if we were to measure their angles, like the measurement of this angle right here in the top left-hand corner would be the same measurement as this angle up here in the top left-hand corner of this figure. So I am going to highlight my corresponding sides. So it is very clear that this side of 5.5 corresponds to this side here for x, which is what I'm going to solve for. And then it's also very obvious that this, what I would call the base of the parallelogram, corresponds to the base of this parallelogram over here. And unlike last time, we're going from a smaller image to a bigger shape, sorry, a smaller shape to a bigger shape. Which means that when we figure out what is the scale factor, what are we multiplying by, we are going to be multiplying by some sort of whole number. And so unlike last time, if I look between my corresponding sides, it might be easier for me to figure out what the scale factor is. And I may not even need to have to set up a proportion. So for example, if I look from 11 to 13, I know, because with proportions, remember, we're always increasing or decreasing by multiplying or dividing. We are not going to use adding or subtracting when we're talking about something that's proportional. So to go from 11 to 13, I know I have to multiply that times 3. 11 times 3 is going to get me 33. And since I'm telling you that these two are similar figures, in order to figure out what x is equivalent to, I'm just going to multiply 5.5 times 3. And that's going to tell me what my value for x is equal to. Sorry, what's it called? It defocused for a second. So if I do 5.5 times 3, I'm going to be able to figure out the value for x. And 5.5 times 3 is equal to 16.5. So that means that this value for x right here should be 16.5. So in this case, I didn't really need to set up a proportion. If you are asked to set up a proportion, you would set it up just like how we did before. So you would take your corresponding sides. So I'm going to do 5. I'll show you so that way you can see, and you'll notice we're going to get the same answer. It's a longer process. Like this is very clearly the easier process, but just so you can see how it works. I'm going to take the smaller numbers and put those as the top of my numerator, and then take the bigger shape and put those as the denominator. So when I'm thinking about the funds process for setting up a proportion, the units in this case are like, what's your smaller figures values and what are your larger figures values? So I'm going to set up my 2 fractions. My units are going to be the smaller triangle. I'm sorry, not triangle. The smaller parallelogram up top, the bigger parallelogram bottom. The numbers, I have 5.5 compared to x, and then I have 11 compared to 33. And now if I solve, this is kind of like last time, I could try to use the Crossroads method, but it's not quite as obvious. So I'm going to use the cross multiplication strategy. And what ends up happening if I do that is 5.5 times 33 is equal to 181.5. And 11 times x is equal to 11x. If I use the division property of equality, 181.5 divided by 11 is equal to 16.5, which is the same thing we got before. And you guys could, you know, if you want to do the division off on the side to confirm that, you can. But I'm telling you, it's right. So this is the way we would set up the proportion to solve. But sometimes that's not necessary. You can identify what the scale factor is and just clearly multiply by it to figure out the missing piece. If this was flipped, like if this was the first shape, if we were going from 33 to 11, the scale factor would be 1/3 because we would have to divide it by 3. And it's really important to note with scale factor, we're always multiplying. So even if it's something where you notice like, oh, I have to divide, if that's kind of what's coming to your head, just know, okay, well, if I have to divide by something, then that means the scale factor is whatever that fraction is. So in this case, we're taking this particular parallelogram and we're tripling it in size. The scale factor is 3. We're making it 3 times its size. But if these two were flipped, if the bigger shape was on the first side and the smaller shape was on the second side, we would be taking 1/3 of its size. We would be decreasing it by a factor of 3. So this is how you can set up proportions using some geometry figures. So your entire homework is just going to give you 2 similar figures and ask you to find the missing sides. So please refer to either of these methods depending on the problem on your homework. And I hope you guys all have an excellent day.